Let us begin our journey. We are about to delve into the fundamentals of cementing, its primary goal, and repair solutions. We will further analyze the difficulties and conventional procedures in relation to cementing operations. Let us start. Cementing is a critical element in oil and gas operations which helps finalize the isolation initiated with casing. Benefits of cementing include pressure isolation, external corrosion protection, pipe protection and support, load application support, such as leak-off and water influx prevention, and pressure regulation. With the use of cementing techniques, we are better equipped to carry out several operations in the oil and gas industry. Cementing is a necessary task for finishing an oil well successfully. Primary cementing is utilized to initially separate the well from the formation and to secure the casing and the casing shoe. This process generally costs about 5% of the entire cost of the well. Nevertheless, in some cases, additional or restoration operations could be needed, for example squeeze cementing. Squeeze cementing can raise the total cost of the cementing procedure up to 17%. Typically, 3 squeezes are required to resolve an issue caused by a primary cement job. Cementing is an important part of drilling a well. The cement needs to be of the right density, pressure and bond in order to create a strong seal. It is also important to ensure the correct pump time, flow loss control, correct volumes, pumpability and cement strength development are taken into consideration to make sure the entire casing is cemented properly. Cementing involves injecting a special mixture, referred to as cement, into a wellbore to create a stable base between the rock formation and the interior of the wellbore. Its aim is to ensure that the wellbore is secure and isolated from other zones and reservoirs, whilst providing a tighter seal to stop unwanted fluid movement. Calculating the equivalent circulating density, ECD, is essential when cementing, as it is the pressure needed to displace the mud from the wellbore and guarantee that the cement gets to the right places. For this wellbore, the ECD is 16 ppg and the effective mud weight is 18 ppg. However, cement is notoriously viscous and dense, making it difficult to ensure full displacement. Cementing basics is a vital part of oil and gas operations. This slide will go over 2 types of cementing: primary cementing and repair, squeeze cementing. In primary cementing, the cement is normally pumped up the annulus at least 200 to 500 feet above the shoe. However, it is unlikely that the cement will reach the surface for a few reasons. Firstly, the fracture gradient is usually 0.7 psi per foot and the cement density is 0.85 psi per foot, making it difficult to push the cement to a higher level. Secondly, it can be a lengthy and costly process. And thirdly, if the operators do not understand the protection requirements, it is not a cost-effective approach. Cementing is an essential part of drilling operations, especially when creating new wells. Near the casing shoe, the cemented column has to be strong enough to resist the highest mud weight that is going to be used in the next section that needs to be drilled. After cementing, a shoe test is done to replicate the predicted highest mud weight. If the shoe weakest, it has to be fixed with squeeze cementing. Keeping the shoe secure is the driller's main priority in cementing, as it is crucial for avoiding external corrosion and maintaining the pressure. It is very important to ensure that the cement bonds to the casing at the right height to prevent failure of the well. Cementing is an essential part of wellbore construction. Primary cementing involves installing cement between the formation and the casing to create a permanent bond and provide zonal isolation. In order to ensure proper performance, the cement slurry must be tailored to the specific conditions of the wellbore. Adding additives to the slurry can improve performance characteristics, such as pumpability and stability. When the primary cement job does not provide adequate zonal isolation, a repair, squeeze, cementing job can be performed. Low-density slurry is injected into the annulus between the defective primary job and the casing. Additives can be added to the squeeze job to enhance bonding, stability, and fluid loss control. 8 primary types of cement exist that are used in different applications. Type A is suitable for surface and shallow applications at temperatures of up to 110 degrees Fahrenheit. Type B has a finer grind, making it ideal for depths of up to 6,000 feet and temperatures of up to 140 degrees Fahrenheit. Type C is designed for high temperature and pressure environments and can be used at depths of up to 10,000 feet. Types D, E, F, G, H, and J are the most suitable for extreme depths and temperatures and require the addition of additives to be used in various environments. Cementing is an essential part of any oil and gas well construction. In this slide we will be talking about 2 types of cementing. Primary cementing and repair, squeeze cementing. Primary cementing is used to set and secure the production casing in place. On the other hand, repair, squeeze cementing, is used to repair and fix any issues that may arise. When creating cement slurry, it is important to keep the density between 11 and 18 pounds per gallon. Adding more water than this may result in weaker cement, leading to channels or weak cement. To accurately determine the fluid density, we use fluid density balance. Cementing basics require taking into account temperature and pressure extremes in every cement design. Low temperatures can slow down cement set time, while higher temperatures can accelerate it. Knowing this is essential when planning a cementing job. The temperature versus TVDS's chart reveals several interesting points. There is a slush zone with a top and bottom, and a permafrost zone with a top and bottom. Additionally, the Alaska well has notable impacts on the temperature profile. This chart provides a deeper understanding of the intricate nature of cementing and how it is essential for oil and gas wells to be successful. Today we will be discussing the modifying the set time of the slurry and how various factors can affect this. Accelerators such as calcium chloride, sodium chloride and gypsum can help speed up the set time, while retarders such as lignins, sugars, cellulose, certain drilling muds and sodium chloride can slow down the set time. The effect of mud on the set time is unpredictable, so this is something to keep in mind. Today, we'll be discussing cementing basics. In particular, primary cementing and repair, or squeeze cementing. This type of cementing is done to ensure that a secure bond is formed between the casing and the formation. If cementing is not performed properly, it can lead to failure of the cement and casing. It is important to note that when using a cement without a retarder, in a hot formation, the cement will set up too quickly, often before it has been completely displaced. Additionally, increasing temperature will make the cement set up more quickly. Therefore, it is essential to take into account these factors when performing cementing operations. It is essential to keep several key points in mind when considering cementing. Well control until the cement sets is an important factor to consider, as is ensuring the pumpability of the cement to displace it properly. Additionally, eliminating the mud cake helps the cement to form a seal with the formation. Furthermore, fluid loss control is essential, as dehydration can prevent the cement from being pumped. Finally, communication must be carefully monitored, and any natural fractures in the pay must be watched out for, to ensure successful cementing. Well control is a very important factor to consider when cementing basics. To guarantee the wellbore is stable, the lower limit of the slurry density should be equal to the pore pressure and also to the wellbore stability. Additionally, the upper limit of the slurry density should be equal to the fracturing gradient. The cement density is normally 16.4 pounds per gallon, while lightweight cements range from 11 to 12 pounds per gallon, with heavier weights up to 23 pounds per gallon. Cementing is a practice employed in many industries for the purpose of permanently bonding two materials together. Primary cementing and repair squeeze cementing are two basic types of cementing. To produce a lighter weight cement, 3 methods can be used: adding more water, using a finer grind cement, or incorporating light weight fillers like ceramics or glass. Foamed cement is also an option. We are discussing the basics of cementing, with a focus on heavyweight cement. Heavyweight cement has a density of up to 23 plus lbs per gallon and can include elements such as sand, hematite, and iron carbonate. However, there are potential risks associated with heavyweight cementing, including frac pressure, equivalent circulating density, cement set times, and fluid loss. It is essential to be conscious of these potential risks before deciding on heavyweight cementing. When cementing, potential problems and failures that may arise include cement at the shoe being too weak, casing not being centralized, cement mixed with too much water, casing not being moved during cementing, and not enough cement in the annulus to act as a barrier. It is essential to be aware of these potential issues so that they can be addressed and prevented. Cementing basics are an important topic of discussion. The effectiveness of the cement used for primary cementing, repair, or squeeze cementing is a significant factor in extending the life of a well without leakage. The chart shows that even after years of well life prior to casing leaks, the rate of failure is very low, such as the 0.25% failure rate for Vastar Putnam wells between 1958 to 1970. This demonstrates the importance of using the right techniques in cementing to guarantee a long, reliable well life. Cementing basics is a critical procedure to make sure that the well is sealed and secured effectively. Possible pollutants and procedures that can reduce cement bond consist of slurry contamination during displacement, failing to clear away the mud cake, sulfate impact on mixing slurry and set cement, acids such as HCl and HF, and explosives employed for perforating. It is important to note that typically, if the cement job fails after a well intervention, it is due to a present mud channel in the cement being disrupted. Cementing is a critical process in oil and gas wells, designed to isolate and contain sections of the well. In this overview, two cementing operations will be explained. Primary cementing and repair or squeeze cementing. To achieve successful primary cementing, the cement slurry must be formulated with the right strength and density to displace and contain the drilling fluid in the annulus. During displacement, fluid loss rate may increase, so the cement slurry must be engineered to mitigate this effect. The challenges associated with cementing in low-strength formations are extensive. These formations have a low fracture gradient and can create natural fractures that can act as thief zones, leading to a reduction in the annulus height. These natural fractures can also serve as fluid loss sites, resulting in dehydration of the cement slurry. Consequently, extra steps must be taken to ensure that the cementing process is properly done. We need to be aware of the potential for fluid loss through natural fractures when carrying out primary cementing operations. To prevent the cement from escaping the wellbore, fluid loss control additives should be used. These additives could be particulate or flake materials, both of which are designed to decrease fluid flow through fractures. It is necessary to include these additives in the cement mix to guarantee the success of the cement job. Cementing plays a key role in drilling and erecting wells. Salt-bearing layers can create gaps or holes that can put the structural dependability of the well at risk. Therefore, when cementing in salt-bearing layers, the amount of salt in the mixture should be monitored as it can speed up or slow down the cement's hardening. Ensuring accurate pumpability and the soundness of the well is essential. Cement displacement is a key point to consider when cementing. Mud contamination is the main cause of cement not setting properly. Sources of contamination are the mud system in the annulus, the inside of the pipe, open-hole filter cake, washouts and cavities. To avoid contamination, it is essential to comprehend the various techniques used to displace the mud and guarantee a successful cement job. Cementing involves inserting cement into the area between the casing and the formation, in order to protect the wellbore from the pressure and corrosive effects of the formation. Primary cementing is done when the well is first completed, and repair cementing, or squeeze cementing, is employed when an existing wellbore needs to be restored. Before cementing, basic mud cake removal is required and can be achieved using mechanical methods like rotation, reciprocation and scratchers, or chemical methods like dispersants, sweeps and solvents. Cementing is a critical component of drilling operations, and it is imperative to understand the fundamentals. Primary cementing seeks to guarantee full coverage and protection of the casing within the borehole, avoiding the passage of gas and oil between the interstices. Repair cementing, also known as squeeze cementing, is focused on filling the annular spaces with new cement to prevent further losses. Mechanical extraction tools such as scratchers and scrapers require the manipulation of the pipe, yet in cases of intense torque and drag this may not be a feasible option. Consequently, these instruments may not be suitable for well repairs. Cementing is a process used to secure casing inside a well bore, and it can be divided into two categories: primary cementing and repair, squeeze cementing. In primary cementing, a mix of chemicals and a fluid is deployed to create a flush in order to guarantee good contact and mixing time with the casing. This flush comprises of a base fluid, a dispersant to mix up cement particles, a sweep to make sure that the cement has properly adhered to the casing, a spacer, and eventually the cement itself. During displacement, it is critical to prevent contamination of the cement. If time of contact, fluid mixing, solids lifting and cement contamination avoidance are all taken into consideration, the flush can be designed in the right manner, thereby ensuring that the casing is securely fixed. When it comes to cementing, the design of displacement and pills is highly important. If the design is inadequate, the drill fluid may not be dispersed or thinned as needed, or debris and other objects may not be able to be lifted out. Moreover, displacement and pill design should be able to remove mud cake, pipe dope, and scale, and effectively push the mud out so that clean cement will be able to reach the desired height. For more information about this, you should check out WellCert. No greetings or thanks needed. We are discussing cementing basics and repair, otherwise known as squeeze cementing. The first step is to use a thinning base fluid flush. An effective brine transition system must then be used to thin and strip the mud, followed by a carrier spacer which will help sweep out solids and remove any coating from the pipe or rock. A separation spacer will do the final cleaning and separate any residual mud from the brine. Finally, brine must be used to sweep out the spacer and leave the well clean. Fluid loss is likely to be high at this point. Cementing is a process used to fill in the annular space between the casing and the wellbore with a cement mixture in order to provide support to the casing and seal the formation. Cleaning and transition spacers are used during the cementing process to separate different types of fluids, as well as remove cuttings, mud, brine, and other solids from the wellbore. The minimum coverage through use of these spacers ranges from 250 to 1,500 feet, depending on spacer type. For instance, the minimum coverage for use of a viscous pill spacer is between 500 and 1,500 feet. A separation spacer for water-based mud and brine requires 500 to 1,000 feet, and for a completion fluid spacer, the minimum coverage is 9 to 5/8 of an inch of casing in a 12-1/4 inch hole, with an annular area of 0.3 square feet. When pumping cement into the well, we must consider the contact time of the cement with the formation. Contact time is the amount of time it takes for a given amount of cement to travel down the well and reach a certain point of the formation. For the purpose of this presentation, we will use the parameters listed in the slide for 8, 10 and 12 barrel per minute pump rate, as well as a casing of 9-5/8 in a 12-1/4 hole with an annular area of 0.3 square feet. The results are presented in the table. The contact time in minutes of a given amount of cement is listed for each barrel pumped and each foot of annular length. For example, if a pump rate of 10 barrels per minute is used, for 200 barrels pumped, the contact time on 1 foot of annular length would be 40 minutes. Today, I'm going to talk about cementing basics and how to use it to repair a well through squeeze cementing. As part of the process, we need to remove the mud cake to clean the well. We have seen that 80% of the outer layer of the cake can be removed without affecting the fluid loss. To do so, we can use a velocity of 300 feet per minute or 92 meters per minute to be even more effective with a dispersant. The flow profile in a well with decentralized pipe is an important factor to consider when cementing. We can see that most of the flow comes along the top of the pipe, which can affect the cleanup and residence time of the fluid on the wellbore. The lower section of the wellbore could remain buried in cuttings and, as a result, never have contact with the circulated fluids. To avoid this, the pipe must be centralized and the pipe can be rotated, as well as reciprocated, to increase the efficiency of the pumping operations. This will ensure that the major flow area within the pipe is maximizing the fluid flow and that the velocity of movement is not too low. Cementing basics is a method of providing the foundations for a variety of projects. It can be divided into two sections: primary cementing and repair squeeze cementing. When carrying out primary cementing, it is important to ensure that the complete borehole is being circulated evenly to prevent any channeling in the cement. To verify this, markers such as dyes, grains, colored beads and others are used. The progress of the markers should be monitored and compared to the calculated sweep, as markers arriving at the surface quicker than expected indicate the whole sweep is not sufficient. Conversely, if the markers take approximately the same time as was calculated, it can be assumed that the whole circulation is adequate. Cementing basics is a key element of any well construction project because it seals the wellbore to avoid fluid exchange between the formation and the wellbore. Primary cementing, also referred to as conventional cementing, is employed to move fluids and mud cake in the annulus for positioning of the casing in the wellbore. When the casing is being installed, the annular space decreases as the size of the drill string reduces, leading to an increased velocity of fluid displacement. In some cases, flow rates need to be lessened to avoid high equivalent circulating densities, ECDs. Pumping down the casing and up the limited annulus may cause exorbitant friction pressure and, as such, high bottom hole pressure, BHP. Regarding cement displacement in a pipe, the two-plug displacement system patented and used since 1915 is the main method. It ensures a secure and safe cementing job by setting two plugs, one to separate the mud from the cement slurry and a second to separate the slurry from the annulus. This guarantees a successful cement job which is designed to last. For primary cementing, the cement head consists of a quick change cap, a top valve, a middle valve, and a bottom valve, which is connected to the cement truck via wiper plug and retainers. Afterwards, a double plug is screwed to the casing. In repair, squeeze cementing, the equipment used is similar, except a float collar is used instead of the quick change cap. Cementing basics is an essential process in the oil and gas industry. It involves both primary cementing and repair, commonly referred to as squeeze cementing. Primary cementing involves the placement of cement above and below the casing to inhibit the migration of fluids and gas. Repair or squeeze cementing involves using cement to mend a broken or wrongly installed part of the casing. The process is conducted using a single wiper plug dropping tool, which has a bail release system. It should be completed with utmost care to guarantee stability and avoid harm to the encompassing casing. Cementing basics is the process of placing a cement mixture along the outside of a casing string to provide a subterranean barrier. This barrier can protect the wellbore from fluid migration and aid the casing in resisting external pressures. There are two types of cementing: primary cementing and repair, squeeze cementing. The two-plug system is used to separate the cement from the mud and displacement fluid. The top plug is solid while the bottom plug is hollow and has a diaphragm that breaks when it reaches the float collar. It is essential that the plugs are not accidentally switched, as this will block the cement from leaving the casing. To prevent this from happening, the two plugs have distinct colors. Cementing is vital for the construction of a well. Insufficient cementing can endanger the soundness of the entire well structure. Primary cementing is the process of injecting cement into the gap between the casing and the rock formations. After that, the cement must be allowed to harden to form a permanent boundary between the two elements. In some cases, it might be necessary to fix the cement, or squeeze it, through pumping extra cement. This will add additional safety against any possible movement of liquid in the annulus. When it comes to well building, cementing basics is an essential concept. In primary cementing, a float valve is used to permit the filling of the casing when it is entered. Upon the pumping of the cement, this valve must shut to forestall any U-tubing. In cases such as repair squeeze cementing, this valve is employed to ensure a regulated influx of formation fluids during squeeze treatments. Cementing is a crucial procedure in the oil and gas industry to guarantee no cross-contamination between the well bore and the surrounding zone. In the primary cementing process, float collars are inserted 1 to 3 joints above the bottom of the casing, to help contain any soiled cement inside the pipe, thus allowing easier drilling out later. Repair cementing, or squeeze cementing, operates likewise but serves to fix a well that already has cement, usually being more intricate than solely cementing a well in the beginning. Cementing basics is a process of placing a mixture of cement and water around a casing to halt the flow of fluids between the casing and the wellbore wall. It is a pivotal part of well construction. For primary cementing and repair, squeeze cementing, multiple pieces of equipment are employed in the bottom hole assembly, BHA, including float equipment and a guide shoe. The float equipment blocks the flow of cement after full displacement, and the guide shoe assists in guiding the casing past ledges and rapid changes in hole direction. Cementing basics is an essential process that ensures the well's integrity. The first step in any successful cementing job is to make sure the wellbore is clean and clear of debris. The next step is to secure the float collar on the bottom of the casing. The float collar is a specialized valve that prevents backflow of fluids and can help to guarantee that the cement is placed in the right spot. It is important to make sure the element wear is not too great during pumping, as this can cause cementing failures. Even if the primary cement job is successful, it is important to hold pressure on the well for some time to ensure the cement has been displaced correctly. Good morning. Centralizers improve the ability of the cement to surround the pipe, displacement the mud to create a channel-free seal and assist running casing in deviated sections. In some circumstances, mud channels can remain, requiring squeezing to ensure a seal. That's what we call repair squeeze cementing. This is a key principle of cementing basics. Cementing basics is an important topic to understand. Primary cementing is when the casing is inserted and covered with cement in the wellbore. Squeeze cementing is when cement is used to repair a badly placed casing. Bowspring centralizers are commonly used, however they may not provide adequate centralization in deviated wells, due to their deformable but weak structure. Therefore, additional measures must be taken to ensure proper centralization of the casing string. Cementing is a crucial process in the oil and gas sector. Primary cementing is used to firmly secure the string of casings in the wellbore by filling the gap between the wellbore wall and the casing. This step additionally allows for mechanical and hydraulic segregation of the casing from the wellbore wall. In repair, squeeze cementing, rigid, solid-body casing centralizers with straight vanes are deployed. This is a slip-over type that drifts between the couplings, unless lock rings are added. The efficiency of keeping the casing away from the wall hinges on whether the formation wall is stout enough to avert embedment of the centralizer into the formation face. Spiral centralizers can be utilized to enhance the performance of cement isolation operations. By minimizing drag and properly positioning the casing, they aid in creating a brief swirl current downstream, facilitating cement to settle in for a superior bond. To cement our knowledge on squeeze cementing and repair basics, I have a quiz for you. The first question is to calculate the volume of spacer needed for a 10,000 feet deep well with a bottom 3,500 feet open hole interval, given a pump rate of 4 bpm, a drilled hole size of 10.75, and a casing size of 8.675, with the needed contact time being 10 minutes and couplings ignored. The second question is, given the volume of the hole being circulated as in the first problem, what percentage of the neutral density tracer appears at the surface 15 minutes ahead of schedule? I hope these questions are useful for you and thank you for your attention.